Welcome to the Explainer. Today, we are diving into the world of randomness. I mean, have you ever really stopped to think about how a casino can build a $1 billion empire on games of, well, pure chance? It's not magic, it's math. And today, we're going to break down exactly how they do it, how you can make sense of the unpredictable. Yeah, that's the big question, isn't it? And the secret, it's not about rigging the games or some kind of sleight of hand. It's about understanding the math behind them so perfectly that they can predict the average outcome over thousands and thousands of plays. It all starts with a few really powerful tools that we're about to get into.
Okay, so first things first, if we're going to analyze the randomness, we can't really work with fuzzy ideas like heads or tails. We need a way to turn those messy, real-world results into clean, simple numbers. Something we can actually plug into an equation. So let's build this idea from the ground up with a super simple example. Just imagine flipping a regular coin 3 times. Sounds easy, right? But that little experiment actually gives us 8 totally different possible outcomes, everything from all heads to all tails. Now, to make any sense of this, we use a nifty tool called a random variable. It sounds way more complicated than it is. It's really just a rule for sticking a number on each outcome. So here, our random variable, which we'll call x, is just the number of heads. See how heads, heads, tails gets mapped to the number 2? We've just translated our experiment into the language of math. And this is the absolutely crucial first step. The formal definition is that a random variable is a mapping from a sample space to the real number line. But in plain English, it's the bridge. It's the thing that takes a random event, like getting HHT, and turns it into a piece of data we can actually measure, like the number 2. Okay, so we've got our outcomes turned into numbers. What's next? Well, the obvious question is, how likely is each one of those numbers to pop up? This is where we start creating a kind of blueprint for the randomness itself. So we build what's called a probability mass function, or just PMF for short. The best way to think about it is like a complete probability map for our random variable. This table shows you the exact probability for each number. So, for instance, the probability of getting exactly 2 heads is 3 out of 8. Why? Because there are 3 different ways that can happen out of 8 total possibilities. And this is where it gets really interesting, when you can actually see the PMF. This bar chart just makes it all click, doesn't it? You can immediately tell that getting 0 heads or 3 heads is pretty rare. All the action is happening around getting 1 or 2 heads. This visual shape of the probabilities is key to understanding how the whole system behaves. All right, so now that we have this complete map of the probabilities, we can ask the most common, most powerful question in all of statistics. On average, what result should we actually expect to see? We're looking for the center of gravity of our whole random experiment. We figure this out using something called the expected value. Now, what's really important is that this isn't just a simple average, it's a weighted average. We take each possible outcome, like getting 0 heads or 1 head, and we multiply it by its exact probability. Then we just add all those little pieces together. And when we run the numbers for our 3-coin flip experiment, the expected value comes out to 1.5 heads. Now that number, 1.5, represents the mathematical center of gravity for our probability map. But hold on a second, I know what you're thinking. You can't get 1.5 heads. That's impossible, right? And you're right, but that's not what the expected value means. It's not a prediction for a single try. It's the theoretical average you'd get if you did this experiment thousands or even millions of times. So knowing the average is great, but it really doesn't tell us the whole story. You could have 2 games with the exact same average outcome, but they could feel completely different to play. So we also need a way to measure how spread out all the results are. Just think about it from a player's perspective. On the left, you've got a predictable, low-risk game. The wins and losses are pretty small, and the results are always hovering close to the average. But on the right, you've got a wild game where the results are all over the place. That's high risk, but it's also where you get that thrill of a huge, totally unexpected win. So, how do we measure this? Well, we use a concept called variance. It's just a single number that tells you how much wobble there is in the system. A low variance means the results are consistent and predictable. A high variance, that means things are chaotic. It's a total roller coaster of risk and reward. All right, enough theory. Let's apply our entire toolkit, the random variable, the PMF, and the expected value, to a real-world example. Let's talk about a classic carnival game called Chuck-a-Luck.
So here's how it works. The rules seem pretty straightforward. You pick a number, let's say you pick 5. The operator rolls 3 dice. If no 5s show up, you lose a pound. If 1 5 shows up, you win a pound. 2 5s gets you 2 pounds, and 3 5s wins you 3. It feels kind of fair, right? Maybe even a little generous. But are the odds really on your side?
Well, we can build a PMF our potential winnings. And once we do the math, a pretty harsh reality starts to set in. The single most likely outcome, with almost a 58% chance, is that you lose your pound. Winning is definitely possible, but each way you can win is less likely than losing. And now for the moment of truth. When we calculate the expected value of our winnings, weighting each win and loss by its probability and adding it all up, we get a negative number. On average, you can expect to lose about 8 pence every single time you play this game. And that, right there, is the secret of the casino. They don't have to cheat. They just have to design a game where the player's expected value is negative. Even if it's just a tiny bit, like 8 pence, that small, predictable mathematical edge turns into a massive, guaranteed profit when it's multiplied over thousands of plays an hour. So, what's the big takeaway from all this? It's that these tools, defining a random variable, mapping its probabilities, calculating its expectation and variance, they aren't just for games. This gives us a powerful lens to analyze and predict the long-term behavior of any system that's ruled by uncertainty, from the stock market to scientific experiments. But, just to leave you with something to chew on, these tools can also lead to some really fascinating, mind-bending paradoxes. Consider this game right here. Its expected payout is literally infinite. So mathematically, you should be willing to pay any amount of money to play it. But would you? Would you bet your life savings on it? It's a fun question that really challenges our intuition about value and risk.